So in our research group, we want to build micro machines and micro robots that can swim in solution. And that is difficult because at small length scales there are no motors or parts that we can just buy. Therefore, whatever we build has to be really simple. And the simplest possible scheme that we can think of is just simply something that expands and contracts, or maybe something that flaps, opens and closes, like in a clam. But the difficulty is that if one builds something that's really small, then this kind of flapping motion doesn't work, because at small length scales, swimming is really different from the kind of swimming that we're used to. And the physics tells us that simple opening and closing doesn't work. And this is known, and it's been known for more than 30 years as the scallop theorem. It's due to Purcell. And the scallop theorem teaches us that these kind of flapping motions do not apply in water. But the interesting thing is that not all liquids are like water, and that is really where our research comes in.
Here, this is a beaker of hyaluronic acid. This is a shear thinning fluid. And when I move the spoon slowly in the fluid, it will be higher resistance. But if I move really fast the spoon in the beaker, it will be lower resistance, so low viscosity at higher speed. Here is the micro swimmer that we built in the shape of a scallop. The width of the scallop is 300 micron. We made this by 3D printing and then micromolding technique. We can control the opening and closing of the scallop by using an external magnetic field. And we can also control the speed of opening and closing of the two shells.
Because of the scallop theorem, this micro robot does not move in water. However, there are fluids other than water that have different properties, so-called non-Newtonian fluids. And they include most fluids one finds in the human body and tissues, such as blood, the vitreous in the eye, and the fluids of the joints.
This is a rheometer. We use this machine to measure the fluid viscosity. We put the fluid in between two moving plates, and by moving the plates, we measure the speed and its torque. By calculating this, we can know the viscosity of different fluids.
So we've heard about how fluids can have different viscosities, and Newtonian fluids have constant viscosities, whereas non-Newtonian fluids can have viscosities that change depending on the shear rate or the speed with which the object moves through them. So instead of using the rheometer to change the fluid properties, we're going to instead use the scallop itself to change the viscosity of the fluid in the area around it. It's best to think of the scallop stroke as being divided into two phases. You have a rapid closing phase and a slow opening phase. And because the shells of the scallop are moving together very quickly during the closing phase, the viscosity within the shell, because we're using a shear thickening fluid in this case, is very large, whereas the viscosity in front of the head of the scallop is relatively low. So we have a net forward propulsion. Now on the opening phase, which is slow, we have relatively low viscosity on both sides. So high shear rates or high speeds result in higher viscosities. And you can see that during the rapid closing phase, the scallop moves forward, and then during the slow opening phase, it moves backwards again. But because of the shear thickening properties, it moves forward more during that forward stroke than it moves back during the backstroke. So the net result is that over many cycles, the scallop moves forward.
This is great news because we can now use really simple actuation schemes, the sort of schemes for which there are many actuators available, like expansion and contraction, opening and closing, to build swimming microrobots that can move through tissue and biomedically relevant fluids.